Okay, so we continue with this chapter of relativistic dynamics. We will begin by a new part of this chapter, which is the collision or relativistic collision, which is a very important part of particle physics. This is the part where we search for new particles, high energy. Of course, they are obtained at a very high energy. That's why the collision is relativistic. So in this part, we search for new particles, for particles that were created at the beginning of the universe, etc. So I will show you some examples of some relativistic collisions used in particle physics. Let us consider a collision between two particles. For example, a particle M1, which is an incident particle, a particle that comes with a certain speed v to hit a target particle named M2, for example. M2 is at rest, is a target, and then M1 comes with a certain speed to hit M2 and to make a collision. The outcome of such a collision, and because it is a high energy collision, could be new particles, M3, M4, and maybe M5, etc. So a high energy collision could create new particles and could keep the same particles M1 and M2. And we will see the difference between the two cases. As in classical mechanics, as in any regular classical Newtonian collision, you always have a conservation of momentum. The total momentum is conserved and the total energy is conserved. Of course, we are considering a system of particles and this system is isolated. So we have no external forces and no external interference. So the total energy is conserved and the total momentum is conserved. So the initial energy before collision, E1 and E2, the sum E1 plus E2 should be equal to the sum of energies after collision. So E3 plus E4 plus E5, etc. And the 3D momentum here is this is the 3D momentum. This is why it is noted by a lowercase p. P1 plus P2, the sum of momentums before collision is equal to the sum of momentums after collision, the 3D collision. Okay, you can minimize these two equations into only one equation, which is a conservation of the 4 momentum or the 4 vector momentum with a capital P. So the initial 4 momentum, the total initial 4 momentum P1 plus P2 before collision is equal to the sum of 4 momentums after collision, P3 plus P4 plus etc. Why the 4 momentum? Because the 4 momentum includes both these equations, because we have the first 3 components, the first 3 coordinates of P are the spatial momentum, Px, Py, Pz, which is represented by this equation. And P0 is the energy, so it is this first equation. So both these equations are included into this only one equation, the conservation of the 4 momentum. Of course, you can use the square of this conservation in order to obtain invariant quantities, because the square is the scalar product of the sum or the vector itself, so it should be invariant. And we always need, as usual, invariant quantities in physics. Also, as in a classical collision, this collision could be elastic or non-elastic. And we will see the difference between the two cases. Okay, so if you have a collision between a mass M1 and a mass M2, that gives you, for example, M3 and M4 after collision. Okay, we have two different cases. If M3 and M4, the particles after collision, are identical, if they are identical to M1 and M2, so this collision is only an exchange of momentum and energy. So this collision is called an elastic collision. It is an elastic collision. So the masses are the same, and we only have an exchange of momentums and energy. So M1 plus M2 will give you, let's say, M1 prime plus M2 prime, of course, with a different momentum and a different energy for each particle, but the sum is conserved. But the masses are conserved. So you have the same particles before and after collision. This is the elastic collision. Another condition or another case, if you have M3 and M4 that are different from M1 and M2, so different masses, different particles. So here you go to high energies, you create new particles. So M3 is different from M1 and M4 is different from M2. So the particles after collision are different from the particles before collision. In this case, the collision is called a non-elastic collision. And that includes disintegration. So when you have a particle, a radioactive particle, one particle that disintegrates into two or more particles, this type of reaction is a non-elastic collision because you have a one mass before collision and you have two or more different masses after collision. So it is a part of the non-elastic collisions. So the difference is clear. If you have the same particles, so it's elastic. If you have different particles, it's a non-elastic collision. And also another important condition into or in the study of collision problems is the choice of reference frames, the choice of the frame. A first choice and obvious choice is to choose a frame that is attached to one of the particles, or that we call the frame R prime. So you have your frame R, the frame, the rest frame, the frame where you put your detectors at rest. Of course, these particles are not observed by naked eye. You need detectors. So the observer here is the detector. So your lab frame is the rest frame where you are putting your detectors. So you have your frame R, the rest frame, and you have a frame R prime that is attached to one of the particles. Let's take an example. Let's say R prime is attached to M2, to the particle number 2. So the initial momentum of 2 is 0. So P prime of 2 is 0 for X, Y, and Z, the first the spatial three coordinates. And you have the energy, of course, it's the rest energy, E prime 2. While for particle M1, for particle number 1, P prime of 1 would be its momentum in this frame, P prime of 1, the three coordinates X, Y, and Z of P prime 1 of particle M1 in this frame R1, and E prime 1, the energy of M1 in frame R prime. Okay, so we need invariants. So the most obvious invariant is a scalar product of P1 and P2. So you take the product P1, P2, and R, which is invariant, so it is equal to P prime 1 times P prime 2 in R prime, because it's the scalar product of the two four momentum vectors of the particles M1 and M2. This is not the only choice of a frame. We have another choice that is mostly used in the study of collisions. It's the frame that is attached to the center of mass of the particle. So you have your system of particles of 2, 3, 4, any number n of particles. And of course, these particles have a center of mass, which is not necessarily a point belonging to one of the masses. You know that from classical mechanics. So we attach a frame to the center of mass and we call it R star or R anything. You can call it whatever you want. So this R star is the frame attached to the center of mass of your system of particles. For example, if you have n particles, the definition of R star, the definition of this frame attached to the center of mass, is that the sum of momentums is always equal to 0 in this frame R star. Of course, this 3 momentum, the 3D momentum. So the sum of momentums is always equal to 0 in your frame R star. And because according to the center of mass, the sum of all momentums is always equal to 0. So the sum of Pi star is equal to 0 by definition of this frame of the center of mass. So in order to better define this frame, we need to find its speed with respect to R. So we need to find the speed of R star with respect to R to see if it is a constant speed and if it is an inertial frame. Because if R star is not inertial, it would not serve us as a proper frame to study collision, because we need inertial frames. So let's find the speed of R star with respect to R. Okay, we will consider as the impulse, the total impulse as a vector along x, or the momentum is along x. So Pi of x star, if we use the Lorentz transformation, okay, so we are using the Lorentz transformation in order to see if it is applicable to this frame. Pi star of x is equal to Pi of x minus v Pi of 0 over radical of 1 minus v squared. And you know by definition that the sum of P star is always 0. So this sum here is 0. So the sum of Pix minus v is the sum of Pi 0 over the radical of 1 minus v squared is equal to 0. So your numerator is equal to 0. And we have here v. So v is the sum of Pix over the sum of Pi 0. And the sum of Pi 0 is the sum of energy. So it's the sum of Ei. It's the total energy. And if you want to arrange your units, and if you are using a frame where c is different from 1, so you have to multiply this equation by c squared. So the velocity or the speed of R star with respect to R is the sum of Pix over the sum of Ei times c squared. Okay, is it a constant speed? You have c squared, which is constant, of course. So what about some sigma Pix and sigma Ei? Sigma Pix is the total momentum. P total, the total momentum P. So obviously this is a constant quantity because it's a conserved quantity. The total momentum is conserved. And the sum of energies, which is the total energy, is also conserved because we are working in an isolated system and you are studying a problem of collision in this isolated system. So total P is conserved and total E is conserved by definition. So these quantities are constant. So sum of Pi over sum of EI times C squared is a constant quantity. So V, the speed of R star with respect to R is a constant quantity. So R star is an inertial frame. R star is inertial, so we are dealing with an inertial frame that we can use into in the study of our collision problems. Okay, so let's take some example. I will consider a particular example, which is a disintegration of a radioactive particles, of a radioactive particle. So if you have a mass M, big M, that disintegrates into two particles, M1 and M2. Of course, you know that the P, total P, 3dP is invariant, and the total energy E, or the sum of energies in this isolated system, is conserved. So this lowercase p, the 3dP, which is equal to P1 plus P2, and E, which is equal to E1 plus E2, these quantities are conserved. So P of big M is equal to P of M1 plus P of M2, and the initial energy of big M is equal to energy of M1 plus the energy of M2, which represents the total energy of the system. Okay, here we have two particular cases. First, if M is at rest, so if the mass M is initially at rest, so P1 plus P2 is equal to 0 because the initial momentum P is equal to 0. And the speed of R star with respect to R would be the sum of PI's, which is 0, so it is 0. In this particular case, R star is the same as R. So you don't have two different frames, R and R star. R star is attached or is the same as your frame R, your rest frame, your lab frame, etc., where you are putting your detectors. If M is moving and if M has a speed, an initial speed V prime, so the speed of R star with respect to R would be the sum of 3dPs over the sum of energy, so P1 plus P2 over E1 plus E2 C squared, which is the total P over the total E C squared, which are the quantities corresponding initially to big M. So it is mv prime over mc squared times c squared. So you can remove the m, you can remove the c squared, so the speed is v prime. Also in this case, R star is the same as a frame attached to M. So it's not the same as R, it's the same as a frame attached to the particle M. And so it is, if you are attaching a frame to big M, so it is a frame attached to the center of mass. So it would be the same as R star. So if M at rest, R star is the same as R. If M is moving, R star is the same as a frame attached to the mass M. Okay? So And we always have, in all cases, in any case, we have the sum of P stars is equal to 0 by definition of the frame R star. So P1 star plus P2 star is always equal to 0. So P1 star should be equal to minus P2 star. So in R star, if you are in this frame attached to the center of mass, you will always see particles ejected in opposite directions in order to respect this conservation of the total momentum. It's the same case we saw previously in the previous session, the disintegration of a positronium, which is or which transforms into two photons ejected in opposite direction. It's the same case. The particles in R star should be ejected in opposite directions in order to have this conservation of momentum. So they are ejected at 180 degrees, the same as the disintegration of a positron. Okay, I will end this session and see you on the next one.